Hi, this is part two of our basic inequalities section in the Maths Olympiad training course. So in this video, we are going to see some sample problems where we'll apply the inequalities that we discussed in the previous video. So we had listed down some of the standard inequalities, AMGM, Cauchy, and also triangle inequality. And what we'll do now is look at some typical problems that will help you solidify your understanding and apply those inequalities in situations. So let's start with the questions. The first one is this one. We basically have A, B, C, D are positive numbers, and we have to show that A plus B plus C by 3 is greater than equal to cube root of 3 ABC, and A plus B plus C plus D by 4 is greater than equal to fourth root of ABCD. Now these are the AMGM inequality for 3 terms and 4 terms respectively, right? So what we want to go about here is we just want to prove these inequalities first, and later we will be using them in different problem situations. So we'll first start with the proof for this, that is easier. So we can say that we know that A plus B by 2 is greater than equal to root AB by the AMGM inequality for two variables. Similarly, C plus D by 2 is greater than equal to root CD. And now I'll apply AMGM to the two terms A plus B by 2 and C plus D by 2. So these are my two terms, and on this if you apply AMGM you'll get A plus B by 2 plus C plus D by 2 by 2 is greater than equal to root over A plus B by 2 multiplied by C plus D by 2. Now, we can use the fact that A plus B by 2 is greater than equal to root AB and C plus D by 2 is greater than equal to root CD by saying here this term is greater than equal to root over root AB into root CD, which is basically equal to fourth root of ABCD, and the LHS becomes A plus B plus C plus D by 4. So we are getting the inequality that we are looking for. We are getting this A plus B plus C plus D by 4. The arithmetic mean is greater than equal to the geometric mean of these four numbers, right? So basically we are using AMGM twice here, once for the standard two term stuff, and then we use AMGM on this combination of terms, and we are able to show this. To show the other one, A plus B plus C by 3 greater than equal to root 3 ABC, in order to do this, we'll apply AMGM on these quantities A, B, C, and cube root of ABC. And we'll use the four-term AMGM identity that we just now proved. So we can say that A plus B plus C plus cube root of ABC by 4 should be greater than equal to root over 4, fourth root of A into B into C into ABC to the power 1 by 3. Now if you think about this here, this is A power 4 by 3, B power 4 by 3, C power 4 by 3 whole to the power 1 by 4. So this becomes ABC to the power 1 by 3, right? So basically we have A plus B plus C plus cube root of ABC divided by 4 is greater than equal to cube root of ABC, right? So simplifying, you cross multiply 4 here and take this to the other side. You will be able to show that A plus B plus C is greater than equal to 3 times cube root of ABC. This is the inequality that we wanted to establish. We can see that A plus B plus C by 3 is greater than equal to cube root of ABC. So with this, we have proved AMGM inequality for 3-term situation and also for 4 terms, right? Let's look at the next question. The question says this: let x1, x2, so on till xn be positive numbers. Show that x1 square by x2 plus x2 square by x3 plus so on till xn minus 1 square by xn plus xn square by x1 is greater than equal to x1 plus x2 plus xn, right? So directly, it seems a little difficult to apply AMGM here directly because we cannot see a very clear pattern here. However, this is an example of a problem where a slight trick helps you quickly do the whole problem very easily. So the trick here is add x1 plus x2 plus xn on both sides. On both sides here. So what we'll end up getting is x1 square by x2 plus x2 square by x3 so on till xn square by x1 plus x1 plus x2 plus xn is greater than equal to 2 times x1 plus x2 plus xn, right? This is the inequality that we'll now try to prove. And why is this good? Because now we can group some terms here. We'll group this term with x2 because it has a denominator x2 and here there is an x2, right? We'll group this term with the x3 term here and we'll group this term with x1, right? So we are saying basically x1 square by x2 plus x2 plus x2 square by x3 plus x3 and so on. There will be n terms from x1 to xn. So xn square by x1 plus x1 is greater than equal to 2x1 plus 2x2 plus so on till 2xn, right? Now the whole inequality, proving this inequality is equivalent to showing that this bracket is greater than equal to 2x2, this bracket is greater than equal to 2x3 and this bracket is greater than equal to 2x1. So basically in general, now we can show that, I'll write it here. If we can show that x1 square by x2 plus x2, actually we can show that this is greater than 2x1 actually, right? Why? Because we can apply AMGM on these two terms. We'll get x1 square by x2 plus x2 by 2 is greater than equal to root over x1 square by x2 into x2. So this x2 gets cancelled and this is equal to x1. So we are easily being able to show by AMGM that this is greater than 2x1. The second term will be greater than 2x2. Similar logic, you can say x2 square by x3 plus x3 by 2 is greater than equal to root over x2 square by x3 multiplied by x3, which is equal to x2. So 2 will come on this side. So we are being able to show that each of these brackets is greater than equal to the corresponding terms here, right? So that's how the inequality is proved. The main idea here is if you simply add an x1 plus x2 plus xn on both sides, then we can use AMGM n times and we are able to prove the whole inequality, right? So hopefully you learned something from this one. Let's go to the next one. Question number 3. In this question, we are given let A, B, C be non-negative real numbers, be non-negative real numbers such that A plus B plus C is equal to 1, and we have to show that 1 plus A multiplied by 1 plus B multiplied by 1 plus C is greater than equal to 8 times 1 minus A, 1 minus B, 1 minus C. Great. So what we can see here, we have 1 plus A, 1 plus B, 1 plus C. So we have to think about how we can get 1 plus A from here, right? So if A plus B plus C is equal to 1, we can say 1 plus A plus B plus C is equal to 2 and 1 plus A is equal to 2 minus B minus C is equal to 1 minus B plus 1 minus C, right? So we are getting that 1 plus A is equal to this, right? Great. Now we know that 1 minus B plus 1 minus C by 2 will be greater than equal to root over 1 minus A 1 minus p into 1 minus c. So therefore, 1 minus p plus 1 minus c is greater than or equal to 2 root over 1 minus p, 1 minus c, right? And this was equal to actually 1 plus a. So what we have shown here is that 1 plus a is greater than or equal to 2 root over 1 minus p multiplied by 1 minus c, right? Following the exact same steps, you can show that 1 plus b is equal to 2 minus c minus a, which is 1 minus c plus 1 minus a, and that is greater than or equal to 2 times root over 1 minus c, 1 minus a, by using AMGM here. So we are getting 1 plus b is greater than this, just like 1 plus a is greater than this. And similarly, you can say that 1 plus c is equal to 2 minus a minus b is equal to 1 minus a plus 1 minus b, and that is greater than or equal to 2 times root over 1 minus a into 1 minus b, right? So we have 1 plus c greater than this. So multiplying these three inequalities, you'll be able to show that 1 plus a multiplied by 1 plus b multiplied by 1 plus c becomes greater than or equal to 2 into 2 into 2, 8. And these terms, there are two of them under the root. So it becomes 1 minus a into 1 minus b into 1 minus c upon multiplying. So I think you can easily see that happening. You should finish the proof now yourself. It is pretty straightforward. Let's go to the next one. Let A, B, C be positive numbers such that A is greater than B square and B is greater than C square. We have to find the maximum value. Find the maximum value of A minus B square multiplied by B minus C square multiplied by C minus A square. Okay. This is the problem. A, B, C are positive numbers such that A is greater than B square and B is greater than C square. Now we have to find maximum value of this. So nothing has been said about C minus A square. So case 1 is if C is less than or equal to A square, then obviously C minus A square is less than or equal to 0, which implies that A minus B square, B minus C square, C minus A square is always less than or equal to 0, right? Basically, the whole product will become negative because the other two factors are positive, but the third one is negative. So there's an upper bound of 0 if C was less than or equal to A square, right? And in case of case 2, if C is greater than A square, right, then we can say A minus B square, B minus C square, and C minus A square. All these three quantities are positive. So by applying AMGM, the product of these three whole to the power 1 by 3 is less than or equal to A minus B square plus B minus C square plus C minus A square whole divided by 3, right? So basically we can say that this product A minus B square, B minus C square, C minus A square is less than or equal to, whole thing here will be raised to the power 3, and we can rewrite this term as A minus A square plus B minus B square plus C minus C square whole divided by 3 power 3, right? Now think about it. We have to find the maximum value of this product, right? So basically we have to find the upper bound of this. So let's think of the function f of x is equal to x minus x square, because here this is a minus a square, b minus b square, c minus c square. What is the maximum value of this function? You can easily complete the square and write it as 1 by 4 minus x minus half whole square. So f of x will be looking like this. So f of x is always less than or equal to 1 by 4, right? If f of x is less than or equal to 1 by 4, that means each of these terms can be having a maximum value of 1 by 4, and that happens when a is equal to b is equal to c is equal to half, right? So you will get this is less than or equal to 1 by 4 plus 1 by 4 plus 1 by 4 by 3 whole cube, right? So that is simply 1 by 4 whole cube, which is equal to 1 by 64. So what we are getting is the upper bound for this is 1 by 64, and that is coming by a straightforward application of AMGM, and also noticing that the terms here are of the form of f of x is x minus x square, which is always upper bounded by 1 by 4. Using that, we can get the maximum value of this, which turns out to be 1 by 64. And that happens when A is equal to B is equal to C is equal to half, right? So that was this one. Let's look at the next problem. Question number 5. Here we have to show that for three non-negative real numbers, three non-negative reals A, B, C that are not all equal, not all equal. We can say that A minus BC whole square plus B minus CA whole square plus C minus AB whole square divided by A minus B whole square plus B minus C whole square plus C minus A whole square is greater than or equal to half. This is what we are trying to prove here. So if I cross multiply and simplify the inequality, it looks somewhat like this. Is greater than or equal to A minus B whole square plus B minus C whole square plus C minus A whole square, right? Now, if you simplify this a little further, expand the terms, you will realize that here also you get basically 2a square plus 2b square plus 2c square minus 2ab minus 2bc minus 2ca. And here also you're getting 2a square plus 2b square plus 2c square. You are also getting plus 2b square c square plus 2c square a square plus 2a square b square and minus 12abc. So just simplifying, you can cancel the first three factors here. So technically the question boils down to proving that we can even cancel the 2 actually, and we have to now show if you cancel the 2, all of these 2's go away, this becomes 6, this 2 goes away, right? So you have to show that b square c square plus c square a square plus a square b square plus ab plus bc plus ca is greater than or equal to 6 abc. This is what is left and this is what we have to prove, right? This is a much simpler thing to prove because we can do direct AMGM on this. How do I do AMGM on this? I can take AMGM for these 6 terms and I can say that we'll have b square c square plus c square a square plus a square b square plus ab plus bc plus ca divided by 6 is greater than or equal to 6th root of b square c square c square a square b square multiplied by ab multiplied by bc multiplied by ca. So the powers here will become 6, right? B power 6, C power 6, A power 6, which is equal to ABC after taking the root, right? So we are easily able to see by AMGM and a little bit of algebra to simplify it that this inequality is valid. This is true, and therefore then we can reverse the steps and prove the original inequality that we started out with. I hope you are understanding how we are applying AMGM here. Correct. So, the next question for us is question number 6, which is let A belongs to 0 to 1 and B belongs to 0 to 1. We have to show that root over a square plus b square plus root over 1 minus a whole square plus b square plus root over a square plus 1 minus b square plus root over 1 minus a whole square plus 1 minus b whole square is greater than equal to 2 root 2. So now this is a question where you can use the triangle inequality. But first let's group the terms together. I'll group this and the last term together. Root over a square plus b square plus root over 1 minus a whole square plus 1 minus b whole square. This is one grouping, and the other grouping is root over 1 minus a whole square plus b square plus root over a square plus 1 minus b whole square. These are the two groupings. And if you look at the first one here, let's draw a figure. Let's say this is point PAB, and this is the origin O, which is 0, 0. And this is the point 1, comma 1, Q. So if you think of this term, root over a square plus b square is the distance of OP. And if you think of this term, that is the distance of 1, 1 from PQ. So that is this term, right? Now we can say that the sum of these two terms or the sum of these two sides is always greater than the third side, right? And if you see here, what is the third side length? It is root over 1 minus 0 whole square plus 1 minus 0 whole square. So that is equal to actually root 2. So we can say that this bracket is greater than equal to root 2 by triangle inequality, which says that if you have a triangle that is formed between 3 points, the sum of the lengths of any two sides of the triangle is always greater than the third side, right? And similarly here, the diagram is slightly different. This is the distance between 1 comma 0, 1 comma 0, and this is 0 comma 1, and this is point PAB. This distance is basically the first term, 1 minus a whole square plus b square. And this distance is the second term, a square plus 1 minus b whole square. And therefore, the sum of these distances is always greater than the third side's distances. And the third side is basically the hypotenuse here, which is root 2. So this is greater than root 2 plus root 2. Therefore, we have proved the original statement that we wanted to show that the sum of these four distances is greater than equal to 2 root 2. Right? Let's look at one final problem before we conclude this video. This final problem is slightly more advanced than the usual ones. So let's look at this one. Let ABC belong to real and ABC product is 1. We have to show that 1 by A cube B plus C plus 1 by B cube C plus A plus 1 by C cube A plus B is greater than equal to 3 by 2. So using this condition, we have to prove that this is greater than equal to 3 by 2. Now if ABC is equal to 1, then 1 by A plus 1 by B plus 1 by C, 1 by C can be written as ABC by A plus ABC by B plus ABC by C. So basically it becomes BC plus CA plus AB. BC plus CA plus AB is equal to 1 by A plus 1 by B plus 1 by C. So that is an important result to keep in mind here. Now, first of all, here, what we'll be trying to do is apply Cauchy's inequality. So we'll be applying Cauchy's inequality to these terms. 1 by A cube B plus C plus 1 by B cube C plus A plus 1 by C cube A plus B multiplied by A into B plus C plus B into C plus A plus C into A plus B. So how are we going to use Cauchy's here? So I'll just do it here. 1 by A cube B plus C plus 1 by B cube C plus A plus 1 by C cube A plus B multiplied by A into B plus C. Correct. A into B plus C plus B into C plus A plus A C into A plus B. Now what happens here is we have Cauchy's inequality says basically that a1 square plus a2 square plus a3 square multiplied by b1 square plus b2 square plus b3 square is always going to be greater than equal to a1 b1 plus a2 b2 plus a3 b3 whole square, right? This is the Cauchy's inequality for three variables. Now here we will take a1 as 1 by root of this, a2 as 1 by root of this, and a3 is 1 by root of c cube a plus b. Now similarly, what is my b1? b1 is root over a into b plus c. b2 is root over b into c plus a, and root b3, that is root over c into a plus b. Now using this identity, we are basically saying this is a1 square plus a2 square plus a3 square, and this is b1 square plus b2 square plus b3 square. That must be greater than equal to the product of both of them term by term square, right? So basically when you do product of a1 and b1, you will end up getting root of b plus c will cancel, and it is a 3 by 2 in the denominator and a half in the numerator. So you'll end up getting 1 by a plus 1 by b plus 1 by c whole to the power 2, 3, 2 to the power 2. I'm making a mistake. Obviously it is greater than square, right? Now think about this. This is actually simply BC plus CA plus AB, right? So I'll rewrite it here. I'm saying 1 by A cube plus 1 by B cube plus 1 by C cube multiplied by A into B plus C. So that is actually twice of AB plus BC plus CA. If you simplify the second factor, this is coming like this, and that is greater than equal to what we saw, greater than equal to 1 by A plus 1 by B plus 1 by C whole square plus 1 by C whole square, right? Now this can be rewritten as AB plus BC plus CA whole square, right? So if I divide this, I will get 1 by A cube B plus C is greater than equal to AB plus BC plus CA whole square divided by twice of AB plus BC plus CA. Right. So this becomes basically AB plus BC plus CA by 2. Correct? Right. Also, we still need to estimate what is the value of this. So what we can do is we can apply, now that we are done with the Cauchy-Schwarz part, Cauchy's inequality has done its job. We can say AB plus BC plus CA by 3 is greater than equal to cube root of AB into BC into CA. And since ABC is 1, this part is ABC whole square. So that is 1, which is equal to 1. Therefore, we can say AB plus BC plus CA is greater than equal to 3. And that means that our overall inequality is greater than equal to 3 by 2. Right? So we are getting 1 by A cube B plus C plus 1 by B cube C plus A plus 1 by C cube A plus B is greater than equal to 3 by 2. And the way we have gotten it is basically first applying Cauchy and then at the end applying AMGM on the final expression to get a numerical estimate, right? So hopefully you have learned something from these problems, how to apply AMGM and also Cauchy's inequality. We will come back to inequalities again and again through this course because inequalities is a very important part of the Maths Olympiad syllabus. But as we go along, we'll see harder and harder types of inequalities. So the next time we come back to inequalities, it will be slightly more advanced stuff. So stay tuned for that. The next thing we will start in the course is a quick section which reviews the trigonometry that you need for Olympiad maths. So we'll do a quick trigonometry review starting from the next section. Till then, I'll see you next time.